Dr. David Reitzel, and with me tonight is Sarah Vincent and Bill Gruneberg. And also, we have a really terrific show for you. We have a very special guest. Our show features a segment called NASA Scientist U with Dr. Mark Kuchner. He's NASA's Citizen Science Officer, and he's going to tell you about how you can get involved with doing some science, which is a lot of fun. Then as the second half of the show, we will take on showing you a little bit more details. Your computer can contribute all on its own. Bill's going to tell you about that. Sarah's going to tell you about cloud spotting on Mars and how you can go look for clouds on Mars. And I'm going to tell you about Galaxy Zoo and you. It's a lot of you in this because we want to get you involved. Now, first, I want to tell you a little bit about All Space Considered. Of course, it is brought to you by Griffith Observatory, the City of Los Angeles, the Department of Recreation and Parks. And we also like to thank our exclusive nonprofit partner, Griffith Observatory Foundation. All the members and the support they provide really makes programs like this possible. Without the technology they help us get, all the streaming we do, all the special events, our school programs, we could not pull all of that off. So I want to just make sure we thank Griffith Observatory Foundation for everything they do. Well, folks, tonight, like I said, we have a really great show. And Mark, are you there?
I'm here.
Yeah, Mark. Mark is coming to us from, you're all the way over at Goddard. Is that correct?
I live in Rhode Island these days.
Yeah, okay, so you're in Rhode Island. A little bit far for him just to hop in the car and drive up to Griffith Observatory. So instead, we figured we would have a remote guest for the first half of the show. Which kind of works, because what we're talking about is citizen science. It's work you get to do remote on your own computer, and you can contribute. But Mark, how did you get into citizen science? Like, what's your connection to this here?
Oh my gosh. Well, I for a totally different project, I happened to interview Chris Lintott, who founded this thing called Zooniverse, which you guys are going to experiment with later. And I don't know, he got me excited about it, and I thought I would try it out. I thought I would build a project and see what happened just for a lark, and I got addicted to it. So it became my new favorite way to science.
Wow.
So I just turned the ship and just went into it wholeheartedly. Here I am.
Well, that's amazing. Well, folks, we're going to turn the program over to Mark now and let him steer everything. You can run things remotely. We'll take a seat in the audience here so you aren't staring at us on the stage and Mark up above. So take it away, Mark. Let's hear about NASA Scientist U.
Oh, thank you, Dave. So Dave set it up so I can just dive right in. So NASA works with more than 2 million volunteers from around the world. And as I was saying, this is my favorite way to science. more than 500 of those volunteers have become named co-authors on refereed published papers because of their work with NASA science. So what we do is called by many different names. You might hear it called citizen science. That's the name of my job title. Participatory science, amateur science, but whatever you call it, I'm hoping that I'll intrigue you enough that you're going to want to try it out because it's just really fun. So I'm going to give you a little tour of citizen science at NASA, a little crawl through history. And then I'm going to tell you some of my favorite projects that are going on right now that could use your help. So probably the first astronomy citizen science project was created by none other than Sir Edmund Halley of Halley's Comet fame. So, we call it amateur science sometimes, but that doesn't really quite describe everything that's going on because really what made this project special was it was a collaboration between a professional scientist and amateur scientist. So it was a kind of organization involving lots of amateurs and professionals. And Sir Edmund Halley was chasing observations of an eclipse. So for some reason, Sir Edmund Halley wrote all of his S's as F's, but I will translate for you. He said, uh, I caused a small map of England describing the track and bounds thereof to be dispersed all over the kingdom with a request to the curious to observe what they could. He was asking people who were along the path of the eclipse to record some observations and tell him what they saw. So that's the first example that I know of. Of course, it wasn't in comets, but we'll see that eclipses and comets are uh, great occasions for citizen science. The first NASA citizen science project, one of the first, was about comets, ironically. So our Stardust mission, launched in 1999, went over to visit a comet named Wild 2. And its main goal was to collect grains of dust that were flying off the comet. But there was a prediction that among the cometary grains, there would also be grains flying in kind of a perpendicular direction at a different speed from interstellar space. And if anyone could find any of these, they would be the first examples we had of material from beyond the solar system. So the Stardust mission was carrying this stuff called aerogel, which is, you may know, it's this very light material, which is good at trapping dust. If it comes in at 10 kilometers a second, it catches the dust, and the dust leaves a little trail, and then there's often a little speck of that dust at the end of the trail. So the mission sent home a bunch of aerogel with little bits of comet particles in it. And then the science team took images of the aerogel at different depths in the material. And they collected 28 million micrographs of the stuff, within which were about 1 million grains. And somebody somehow estimated that among those million grains, there'd be about 45 of them that might be from interstellar space. How on earth were you going to find these? So Andrew Westphal had the idea, perhaps inspired in a long way by Sir Edmund Halley, he was going to put the micrographs online because now we have the internet. And he put them online, and he asked people to look through these images in the form of what he called focus movies. So he had images of the micrographs from one depth in the material, another in the form of a movie. And the tracks in the aerogel, they might look like lines, or if they were going the right direction through the material, they might look more like what you can see labeled in this image. See, the track points to this kind of circle that's appearing. So anyway, it's pretty easy in these movies to see, once you get used to it, to see whether a track is going, what direction it's going in, if it's going perpendicular to the depth of the focus or what have you. And amazingly, 33,000 volunteers came online, joined this hunt for gold, and they found 8 interstellar grains, which is to this date every single example that we have of material from beyond the solar system. Every sample that we have, these tiny little grains, but they're priceless because that's all we know really about solids from beyond the solar system. And that project was the first NASA citizen science project to really be a hit. And it's still running at Stardust at Home. So Stardust at Home inspired this guy, I think I mentioned, Chris Lintott. So Chris Lintott was studying at Oxford, and so was this other fellow named Kevin Shawinski at the time that Stardust at Home came out. And Kevin had just been assigned by his advisor, his graduate school advisor. Go look through these images of galaxies and classify them. So just write down, is it the galaxy a spiral or is it an elliptical? Kevin went to the basement at Oxford. He started looking through the galaxies and he got tired. And a week later of just looking at galaxies and classifying these galaxies, elliptical, spiral, spiral, elliptical, he told his advisor, enough. I'm not doing a single other galaxy. So luckily, his friend, Chris Lintott, said, hey, what if we make our own Stardust at Home? And they put the galaxies online, just the way that Andrew Westphal had put the Focus movies online. And they started a project called Galaxy Zoo. Galaxy Zoo was another big hit. In fact, more people participated in it than in Stardust at Home. And it's another project that is still running today and pumping out discoveries. That project was so successful that Chris and Kevin went on to start a community, an online community of citizen science projects called Zooniverse, which is now an important partner with NASA. About a third of NASA's citizen science projects are hosted by Zooniverse. So fast forward to today. NASA now has 43 active citizen science projects, participatory science projects online. Something for everyone. They're in all of NASA's science divisions. So NASA, besides astronomy, we do planetary science, heliophysics, earth science, and biological and physical sciences, which is projects that are done in low gravity. So projects on the space station, for example. And every one of those different science divisions has projects in it. There's no need to be a citizen to do a citizen science project. It's probably not a great choice for the name, so I apologize for that. That's what people were using in the community. In fact, we have projects that are available in 18 different languages, encouraging everyone from around the world to join. And we have multiple policies in place at NASA, which ensure that these projects are held to the same rigorous standards as any NASA science project. And that's really important to me personally, because it means that if you come and work on a project, you know you're guaranteed to be working on something that scientists really care about, that's really going to be advancing knowledge, right? So, there are times when you might be working on a science project, right, which is really aimed at your own learning, which is more for fun. These projects, they can be very fun. But what sets a NASA participatory science project apart, I think, these are all projects that are going to have a real big impact on the state of the art of science. So what do our volunteers do? They do anything and everything. They're just spectacular. They bring all kinds of skills and passion, and they're really irreplaceable. So our volunteers have been deploying sensors, measuring air quality and audio backgrounds, building their own radio telescopes. They read and make sense of the professional literature in a variety of different fields. They write their own software. Sometimes people will ask me, well, now that we have all kinds of machine learning and AI, do you still need to do citizen science? And I laugh because our volunteers, yeah, they do their own machine learning and AI. So it's just making everybody faster at once. They take water samples. They save lives. They make artwork. One of our volunteers was part of a discovery that was in a press release, and the press release needed some artwork to go with it. He said, guess what? I'm an artist too. And days later, he had made this spectacular artwork, and it now hangs in a museum. They translate projects and materials into other languages. One of our volunteers introduced the science team, to new professional colleagues who had access to a different observatory that the science team didn't have access to. And then he traveled across South America to go on observing runs. Every time I go to a scientific meeting these days, a professional meeting, I always see our volunteers there. They write papers, I mentioned, research notes, they win prizes. They're involved in every aspect of science, really. So how about what have folks been discovering? Well, our volunteers have come to dominate multiple scientific fields. I think I mentioned that they've discovered every known sample of interstellar material. That work ended up being its own issue of a journal. There was an entire issue of meteoritics and space science devoted to the analysis of those grains. They've discovered most of the known comets. There's no qualifier on that. It's not like most of the green comets, most of the comets were discovered by NASA volunteers. Discovered most of the ultra cool brown dwarfs. Tell you about that a little bit later. A third of Kepler mission's long period exoplanets. The yellowtail star-forming regions, the TP10 special signature for lightning, a rare six-planet transit existing, an asteroid 2 times the moon's distance, first extreme T subdwarfs, aurora and brown dwarf, Zika virus improving in cemetery phase, the oldest white dwarf debris disk, the Dipper star phenomenon, excellent planets and Kepler data, the Meyer family of comets, a transiting planet in Kepler star system, 400,000 Martian seasonal fans, 283,000 emperor penguin nests, 127,000 Martian clouds, 9,120 candidate near-Earth asteroids, 89,000 mosquito breeding sites, 7,000 Jovian vortices, 286 imposter planets, 196 transient luminous events, 164 long-lived solar active regions, 15 active asteroids, 7 meteorites, 5 Peter Pan disks, and 1 new kind of aurora named Steve. And there is a coin on the bottom of that slide with a picture of Steve. It's the purple stripe. It's a new kind of auroral phenomenon. I also have, by the way, Steve socks. I don't know if you can see my face up on your screen there, but Steve is a real point of pride among the Aurora community. So how do you choose a project with all of these projects that are online right now? So on NASA's website, our Citizen Science website, I recommend starting with one of the projects that's called Anyone with a Cell Phone or Laptop Can Do. Of course, later on, you're going to hear about projects that just your computer will do even without you. So maybe there's a whole other category of projects. But, for me, I'm more excited about projects that take advantage of the curiosity and unique human capabilities. I recommend trying one of these projects. That's an anyone with a cell phone or laptop can do project. And then also we have these handy summary pages for most of our projects online now. So you can click on read project summary. And there we've collected a bunch of handy dandy data about what you'll do when you do the project, how old you need to be, what the requirements are, and so on. So that's a great way to get started. And I think you're going to dig into this cloud spotting on Mars project a little bit later. It's a really cool project where you look at data from the Mars Reconnaissance Orbiter and look for these little arcs, which are the reflectance radar signatures from clouds. As the spacecraft goes above and below the horizon, the cloud creates this arc in the data, which you'll look for. All right. Now I'm going to tell you some of my favorite projects that are going on right now and hope to inspire you. So first of all, I've got to mention that our volunteers are helping save lives. So these 2 projects involve taking data on your cell phone. So Landslide Reporter, for example, is building an open database of landslides. So if you see a landslide somewhere, you can pull out your cell phone and enter in anything you know about the landslide, including a photo if you could take one. And that's be used to model and predict future landslides, which is something that we are not very good at yet. Mosquito Habitat Mapper, another earth science project, asks you to take pictures on your phone if you see standing water. And if you see mosquito larvae, even better, take pictures of the larvae, and it'll help you identify what kind of larvae it is. And then when you're done, you've got to dump out the water so the larvae don't grow. But hey, malaria is not a good thing. Zika virus, very bad thing, spread by mosquitoes. And the more we know about how those nasty buggers migrate, the more lives we can save. Backyard World's Planet 9. This is the second project that I started myself when I was starting to get interested in citizen science first. So this project looks at images from NASA's Wide Field Infrared Survey Explorer mission, WISE mission, which imaged the entire sky in infrared wavelengths. So it captured images about 2 billion sources. And among those sources, there may or may not be one Planet 9. So we were hoping to find Planet 9 in there. And in particular, I was interested in finding Planet 9. You've probably heard about it in the news and so on. It's a hypothetical planet that orbits beyond Neptune. It's not Pluto. It's more like a 3 Earth mass planet with an eccentric orbit. And it's thought to shape the distribution of the Kuiper Belt objects. So I was interested in this because my thesis advisor was a man named Michael Brown, and he is still very keen on this Planet 9 hypothesis. So I figured, hey, I'll show Mike. I'll find his planet for him. So, oops. All right. So we put images online from NASA's WISE mission and asked people to help us find Planet 9. And there's so much data on there. We've really only gone through about half of it. But in the meantime, we haven't found Planet 9 yet, but we have discovered more than 4,000 brown dwarfs, which are these objects which they're balls of gas, typically Jupiter-sized, and they're too low mass to sustain hydrogen burning and be stars. And they overlap in many ways with planets, but they also are considered to be more massive than planets. So, and these objects, they're pretty common. So there's one for every 6 stars. So many of the nearest stellar and substellar objects are these brown dwarfs. And the question is there a brown dwarf floating between the sun and Proxima Centauri, for example? We don't know if there's any other object between the solar system and Proxima Centauri. And so we're hoping to detect it with this project. And then here is that illustration of the orbit hypothesized for Planet 9. You'll hear about it if we find it. You'll know. In the meantime, you're welcome to help join the search. This next project, the Sungrazer project, is particularly exciting to me. It's started about the same time as Stardust at Home. So it's one of the earliest NASA projects. And this project started because people were looking through NASA archives from the SOHO mission, and they were seeing objects like the one in that animation you're looking at. Something zipping around, looks a heck of a lot like a comet. And they started pestering the science team. Hey, I think I found a comet in your data. Is this a comet? Is this a comet? And the scientist, Carl Badams, got annoyed by these emails. And he said, hey, you got to do a lot more work to check to see if it's a comet. Here's all the instructions. Here's what you really need to do to better understand the data. And he made this instruction sheet. And after a while, he ended up putting it on the web so that keep people out of his hair. Well, guess what? Turns out people really were finding comets, and Carl got addicted to citizen science, just like I've become. And the Sungrazer project has been going ever since, and it's found most of the known comets in this process. And they just celebrated the discovery of their 5,000th comet. I'll just read that aloud because I love it. More comets have been discovered by the Sun Grazer project than by all other surveys, telescopes, and astronomers combined. So you probably didn't see the aurora last weekend. And, next time I'll try to crank up that solar storm a little higher and maybe get some ions down your way in Los Angeles. But people probably did see it in Northern California. I don't know if anybody made it up north far enough to see it. So here's a picture of an aurora at Mammoth Lakes, Northern California. Anyway, if you saw the aurora, we need your photo. So we have this project called aurorasaurus.org. That's the one that discovered Steve. And it keeps track of where people see the aurora and compares it to models, predictions for where people should see the aurora, and uses everybody's observations to refine those models. That should help us predict future solar storms, which can have quite dangerous consequences. You've probably been reading about it in the paper. Also, another astronomical event that I apologize we couldn't go through California, the eclipse. So April 8th, there's this great total solar eclipse. Maybe some of you traveled to see it. So we've come a long way since Halley distributed those maps. And this year we had 36,000 volunteers, more than 36,000 volunteers, who took data for NASA projects on the April 8th total solar eclipse. That's one of the images captured by our volunteers with a DSLR. And by the way, these projects are still combing through the massive amounts of data that they got. So for example, Eclipse Soundscapes, one of our Eclipse projects, is announced that they're going to be asking for help analyzing their data. So check back if you're interested in doing some Eclipse science. Also, Eclipse Mega Movie is probably going to need help analyzing their data. So look for calls from NASA. We'll announce it on our social media feeds and so on. I have a couple minutes left, so I'm going to tell you about Burst Chaser, a project which is on Zooniverse. It's asking people to classify. These are the most powerful explosions, in the universe. They're so powerful that we can see them from all the way on the other side of the observable universe. So they're brighter than supernovae. They're probably either explosions of really, really massive stars or crashing together neutron stars. Maybe both those mechanisms work. Anyway, really cool thing to work on if you like things that go boom. I want to mention that more and more of our projects are having regular real-time meetings with volunteers. So besides going on Zooniverse or letting your computer do something, I recommend trying one of these projects. You can see from the summary pages, one of these projects, and go to regular video calls with scientists like me and come talk science with us, come geek out with us. That's how a lot of people are really getting deep into things. We also have this events. SciStarter is running Zoom calls for the public. They're about once every couple months, which are virtual events with NASA scientists. And you're invited to come to those and hear about what we're working on, get more involved that way. I wish I could meet all 2 million of our volunteers. I can't. I've gotten to know a few of them. I'm going to tell you the story of Michaela Allen, who got involved in NASA science. And she said, this project is what made me to change my major to physics and made me want to do research in astronomy. So she was a business major, and now she's gone to graduate school in astronomy. Very excited about that. And she says it's because of working with us. And here's a picture of Danny Roylance, who got involved in a earlier NASA citizen science project, and he was so outstanding on that project that he was asked to join the science team for the Burst Chaser project. And here he is working with the PI of Burst Chaser. So he's just a outstanding contributor. And I met him at a scientific conference this spring. And he took me aside and he said, I never got to tell you this, but did you know that I'm an Army veteran? I've been struggling with PTSD. And he said, I went from not being able to take the garbage out because he was at this horrible low point in his life. He didn't even want to go out the door, to flying to this meeting in Phoenix last month to present that poster. My growing citizen science activity has become stronger than my fears. So come join us. Head to science.nasa.gov/citizen science. I say search for a project that's anyone can do anywhere. Check out the summary page for more info, or just go right to the project website and dive right in. And if I can be of any use, send me an email. Thanks so much for having me.
Yay. There he is. So now our audience can see you. Our audience in the theater was just seeing your slides most of the time.
Oh,
but our audience
you didn't get
online.
To see my Aurorasaurus.
Exactly. So I wanted to have you show. Exactly. I figured
Nice.
I'd mention that here so our audience in the theater could see your socks, but online they were able to see them earlier.
Okay.
But I have a question for you on this. With the first couple of projects, were people skeptical that the results that were going to come out of these projects would be good? Were they worried that the citizens would be pranksters or would do bad science, just to have a laugh?
Yes. Yeah. Well, first of all, not citizens. No citizenship required. The projects are open to everyone. There was a lot of mistrust. In fact, I still sometimes get pushback. People say, "Well, that's not. How can you trust what volunteers are telling you?" But decades of awesome papers later, I think we've changed a lot of minds. We had our first couple of papers in Nature, high impact journal, come out this year. The secret is that whenever you launch a project, you start by going through a beta test phase, right? So you get a couple hundred volunteers that you trust, and we know enough volunteers that we can collect 100 beta testers for a new project, and they try it out and see whether they're getting the data quality that you need, and if you're not, then you make some refinements and test again.
Now, is each person working on the project, are they the only person looking at that particular datum, that bit of data, or is it reviewed by a lot of different people working on the project?
It's reviewed by a lot of people, and that people often find that shocking. So volunteers are often concerned that, oh, shoot, what if I made a mistake? Did I mess up all of science? Did I break, right? And the answer is no. In a project on Zooniverse, you might have 10 or 20 different people who are looking at each galaxy, for example. So there are lots of checks and balances in. And then once there's something that, once you move on to the next stage of analysis, there's so many checks in the scientific process, right? So the science team argues with each other about what the right interpretation is. And then they struggle to write it up and communicate it to a referee who's then going to pick their paper apart and argue about it. And there's just, all those different times when people are going to check it and make sure that it's right, that it's consistent with what we know from other studies. And that's just, I think it gives people much more confidence in science when they see all those checks firsthand, how much it takes, how much checking it takes to get something into the scientific literature.
Right. So does anyone in our audience have any questions? I think he can actually hear you, although we might need to repeat it for the online audience. So what's your question? I'll repeat it.
I have a question that will sound mildly controversial, but I mean it lightly and as a curiosity. You know, sometimes like there'll be like a case that like the police are trying to solve and then they're not able to do it at all. And then like there's witnesses, like community people who solve the crime. And then after, people come out and they go, oh, we want to thank our police officers who maybe didn't do much of the work. Does at all with this, when you're saying like the majority of these discoveries, like in some cases you're saying all of them are made by citizen scientists who may not be formal scientists, does this at all impact the legitimacy of actual scientists? Is there a vibe around that? Like sometimes is there a contention between the scientific professionals that may have like, you know, they get the funding to do the work, and they're just missing. And then some guy in his backyard with a stick who's trying to get over people's heads. Like,
Yeah.
that's
So-
a thing.
So let me repeat the question for the online audience, so I don't think they can hear you quite as well. But the question is essentially the citizen scientists that are out doing the work, does that devalue the work of the scientists at all? The scientists get their funding, they're doing their research, and all of a sudden the discovery is made by these citizen scientists. Is there any contention between there, or is there any issues?
That's a great question. And I love how all the questions are, you're picking up on the fact that what's going on here is a cultural shift, right? We're changing the norms, the culture of science, right? So people have been concerned about that, right? But ultimately, I would say if confident scientists have nothing to fear, right? It's recognized when people put out a paper who is at what stage in their career, and the scientific community is small enough that they really know all of each other anyway, right? So what is changing though, is that often papers are getting long lists of authors when they might have just had a couple. So we have to get scientists used to this idea that instead of sharing authorship with just their grad student, they're now sharing it with 100 people maybe.
Yeah.
And that's confusing to some of my colleagues. But it's not impossible, you know, you just have to spend a little while typing in names and everybody gets their piece of the scientific credit pie, you know?
Yeah, another way go ahead, Mark, sorry.
It's just, it's so worth it. Like, as a scientist, I went in thinking that like, okay, I've got this task and I'm going to have these volunteers do my task, tell me the answer, then it will be done. Not like that, though. That's not what happened. What happens is I have this task. You guys do this task. Well, we did your task, and it turns out that wasn't the right task. Have you considered this? You should do this thing. Hey, by the way, we did that thing. Here's the answer. It's like, it's magic. Real humans with real curiosity take a problem farther than you could ever have done it yourself.
Yes.
And so the one paper that I would have written by myself turns into 10 papers.
Yeah.
Awesome.
Yeah. So I like to think of it also that scientists that are confident don't have any worry in this. The context of how this all fits together still requires a dedication to reading the journals, spending a lifetime of being involved with this. Yet folks that have their own lives, their own loves, their own careers can still contribute. You can go to your computer and you can help out and you can become part of the process and you can dive in as far as you want and make some of these discoveries, but still the scientist that knows the big picture can find out how that fits in and see how it links to other things. So the scientists will never have anything to worry about. In fact, this just lets us do more, in my opinion. This just opens more doors. So, well, folks, we have time for one more question here.
I don't know if you've been watching it, but there were a couple of school kids who got some more proofs with, I think it was the Pythagorean theorem, and we're not mathematicians. We just sat down and we kind of figured it out, and now we're working on a couple of other ones.
Yeah.
That was a fascinating, it's similar to what you've been talking about.
Yeah, for the online audience, the comment was about how there were some school kids that did a Pythagorean proof about how to do that. It was a different way to do it that nobody had ever thought of before, and now they're doing mathematics and involved in it. So there are opportunities everywhere for folks to get involved with this. Well, everyone, we need to change our focus a little bit here, but let's thank our guest again. Thank you so much for joining us, Mark. Really appreciate you. If you're ever here in Los Angeles, come see us at Griffith Observatory, of course, and we'd love to have you here in person if we ever could. So.
Bring my socks.
Bring those socks.
Absolutely,
Yes.
bring the socks. Absolutely. So, all right, folks. So now let's skip past his bonus material here. Went one too far. Okay, here we are. So now you're at home and you might be wondering, how do I get involved? What do I do? I want to do citizen science. How can I do it? Well, Bill.
Yes.
Grab your remote here, and Bill has been doing citizen science for decades now.
Well, almost 20 years.
Almost 20 years,
Yeah.
yeah. Now, but you
don't
don't
look a day over
often,
15.
you do sometimes log in and do a little bit of
I
work
have done
yourself,
that,
but
yeah.
instead you replaced your flying toaster screensavers.
Yeah, sadly.
It was sadly, because everybody misses those, with something called BOINC.
Yeah, BOINC. This is run up at Cal, UC Berkeley. It's the BOINC Open Infrastructure for Network Computing. And what that means is it's distributed computing, just really exactly like the projects you've been hearing about. The difference here, and I've been, as I developed this, we developed this story, I've been sort of jokingly call it the lazy person's way to do citizen science, because you don't have to do anything. I mean, this app actually, will bring in the data, crunch the data, do simulation, whatever needs to be done, and then send it back, and you don't, have to touch anything. You don't even have to look at it. And so it's very useful in that regard, because we can't always be at our computers doing work on, stellar activity or whatever, planetary clouds, whatever. And also, you have a laptop or something, you walk away from it, you go get a cup of coffee, and then I got to wash some dishes, and then you take an hour walk, and you come back and you say, I've wasted all that electricity, but now it will not be a waste anymore, because these screensavers will actually be behind the scenes doing this work. So there are almost 30 projects in this bunch and with BOINC, and I picked out 4 of them because they're the most astronomical, astrophysical, cosmological, and they're really cool projects. But the ones I'm not going to talk about, there's also climate change study, there's disease study, there's some pure mathematical computations that people are putting into this screensaver. So lots and lots and lots of stuff to do. But here are the ones that I...
So what this is doing is you load this on your computer, and then while you're not using it,
Right.
they're doing calculations using your CPU.
You can even set the time lapse between the last time you move the mouse or hit a key or something, and then the screensaver comes up. I've got mine at like 3 seconds, because if I haven't touched it in 3 seconds, I'm probably walking away. And it will just do everything. And so like I say, for 20 years, I've been running these as my screensaver, so I've made some contribution somewhere, I guess. I don't know. And also doing the other kind as well, because that's fun. I actually see the interactive work as almost like gaming. It's actually kind of a game, so it's really fun. All right, I'm going to move forward to this project called Einstein at Home. Well, let's look at Mr. Einstein at home. There he is, sitting on his porch with those big, fluffy, comfortable-looking slippers. But there is an Einstein at Home project, and it looks kind of like this. This studies pulsars. Now, what are pulsars? If you've been to our shows before, you've heard of them. Pulsars are a type of neutron star. Well, what's a neutron star? A neutron star is the aftermath of a supernova of a star that isn't massive enough to make a black hole when its core collapses. The core collapse to a black hole, not big enough. But the core collapse in neutron stars actually turns into almost all neutron material. Atoms get smashed together. So the electrons in their orbits around the nucleus get smashed all the way down to the nucleus. You have positive and negative charges. Those become neutrons, basically. These things are incredibly, incredibly dense. NASA, in fact, on their website says, if you take a teaspoonful of a neutron star, bring it back to Earth and weigh it, 4 billion tons, a teaspoon. So they're amazing objects.
It's a really strong teaspoon, though.
Yeah.
That's right. Yeah, that's exactly right. So you see this one in the image here, the animation. This is when these things become neutron stars, they still spin. In fact, they spin much, much faster than they did as stars because all that spinning energy, which we call angular momentum, is now focused into just a little tiny object like 12 or 13 miles wide, which is really small for a star. And they spin like crazy, up to like 700 something.
But how do they find them?
They find them through if these jets that form, that shoot energy out into space from the poles in these neutron stars, which black holes tend to do too, if they're lined up in such a way that those pulses, hit Earth, then they can be detected and they're found. Now, the ultimate goal in this is to try to associate. Yeah, thank you. We did need to go to that. I'm sorry. This is what you actually see when you're running that beautiful screensaver. But when Einstein. Why do we call it Einstein at home? Because they're trying to find waves in space-time. These waves, from gravitational waves that Einstein predicted. Associated with a neutron star. They have not done that yet, but they have found 90 previously unknown neutron stars. So talk about, contributions. That's a lot of stuff to study.
Yeah. So they're using LIGO data, which is the laser interferometry observatories, gravitational wave observatories. Mm-hmm. Those are looking for sort of the squishing and squeezing of space-time that these pulsars can cause. And they're finding neutron stars, but they haven't linked any gravitational waves.
Not yet. Not to one of these yet. But,
But we need more people involved, it sounds
That's right.
like.
That's right. All right, so the next one we should look at here is asteroids at home. And there is an asteroid at home at Einstein's home in Princeton. When we look at or find asteroids these days, we find them either two ways. One is you take a time exposure space, with a clock drive, so all the stars stay, in one place, but you see a streak across the sky like that. That's either one of Elon Musk's really annoying satellites, or it's an asteroid. But you see on the right here a picture of an asteroid very close. This was the DART mission, which slammed into an asteroid called Didymorphos and tried to alter its orbit and did successfully. It was a very successful mission, which means that we can have some hope. If we do see an object coming toward us, we can very likely divert it, since we've proved we can already do it. If we keep funding NASA, that's the big if. Okay. So, but now here's the thing: using data from professional observatories and even backyard astronomers, this is what this project is doing. It's finding the objects and is able to sort of calculate much more clearly what their shapes are. And Dr. Reitzel, you said you can learn something from these shapes.
If you look at these, you can see some look a little more, like a spinning top. Some might look a little more like a potato. Well, we've flown by asteroids, of course. The one on the left is known as Ida. And see the one that's in between, the little round one in between? That's actually a moon of Ida called Dactyl. So there's a little asteroid orbiting an asteroid. The one on the right, that's actually Bennu. And that's a big rubble pile. You can see it's made of independent little rocks. The one on the left is probably more solid. You can actually see craters on it where things have smashed into it and left behind a crater. So let's go back to those shapes again. The one in the upper left looks a little bit more like Bennu to me, and the ones in the lower right look a little more like Ida. So this tells us maybe a little bit what material they're created of.
Yeah.
And if we need to deflect one, well, it might change how we deflect it.
Right.
We're learning about how to do that with that DART mission you talked about.
That is really awesome. Okay, now we go to Milky Way at home. There's Milky Way sitting at home on its porch with those fluffy slippers.
Yeah.
This is basically what they're trying to do is build with data from the Sloan Digital Sky Survey. You might have heard us talk about that in the past. And they're trying to build a really accurate 3D model of our galaxy. But in the meantime, they also found, they looked at this thing called the Sagittarius Stream. several billion years ago, a smaller galaxy, a dwarf galaxy, got gravitationally pulled into our galaxy, and that turns it into a long stream of stars. And they have kind of recreated what that smaller galaxy was like in terms of mass and structure and all kinds of things. So that's doing some really interesting science too.
So this is all just done while your computer is
You
sitting
don't
there.
have to do a thing.
Okay.
If you're lazy like me, it's perfect. Okay. Last one I'm going to do is the Large Hadron Collider. And there's the Large Hadron Collider. All of these jokes were Dr. Reitzel's idea. I'm so glad he came up with it.
Yeah, although Ella helped pull them off. Yes, I have conspirators.
And they all wear the same fluffy slippers.
Yeah, they're
I
great.
mean, if it ain't broke.
That's right. That's right. So LHC at home, the Large Hadron Collider, what we used to call atom smashers. They get the protons going up to speeds that are near the speed of light, bang them into each other, see what comes out, and learn about matter on a very fundamental scale. But they also do something that is very cosmological. They take lead ions, very heavy ions, and smash them together. And that creates a condition that is very, that we believe existed just after the universe formed, right? I mean, literally a very tiny fraction of a second before it formed, and only lasted for about a millionth of a second. But we can study it because of this, this project at LHC. So that's another one that I recommend taking a look at if you're interested in this. And if you are interested, here are the websites. You can just, Google BOINC and Berkeley. Remember that little E in the middle. Or you can look at this again later, whatever. It's pretty easy to find. And once you get there, it'll just shepherd you right to how to develop, or download that app and how to use it and parameters and everything.
And if you like a lot of different ones, you can have multiple projects going, and it'll cycle through them. You can say, I want this one to run twice as often as this one. You can do everything with them. Well, we need to move on. Otherwise, I'd take some questions from the audience, but we're running a little late tonight. So, oh, no, it's fine, Bill. That was really interesting. But Sarah's turn. Sarah is going to tell us more about that cloud spotting on Mars project that you heard about from Mark, Dr. Kuchner. So, Sarah, what'd you learn about cloud spotting?
Well, I learned because I'm not that lazy person doing, using my screensaver. Thanks, everybody.
Bill's point was to do both.
Lazy people always find the quickest way to do everything. They're incredibly
Work
efficient.
smart, not hard. I can't actually fault that. So, cloud spotting on Mars, it's a really cute, really simple thing. But if you want to get a little bit more interactive with your citizen science, it's also found on Zooniverse. Zooniverse, there's a V in there, not an F. But here's an image of clouds on Mars. This is perhaps what you might be expecting, except Mark did indicate that you'd be looking for arcs. These are not really arcs. The cloud spotting is using data from orbit. And so the cloud spotting app, you have a really quick tutorial that walks you through the different pieces of information that you need, bare minimum to get you started. You can go more in depth later if you want. But there is an arc. Really, really stark arc. I'm rhyming now. Once you finish the tutorial, you'll be labeling those arcs. And if you're wondering why an arc of a cloud, or why a cloud looks like an arc, it's because as the Mars Reconnaissance Orbiter approaches the cloud, it's almost like if you imagine you've got a mast on a ship and you're coming around the curved Earth. You're going to see that top of the mast, and then you'll see more and more of the mast exposed. What you're seeing is sort of the space appearing underneath that cloud and then disappearing as MRO continues passing over it. And so that paints an arc in the data over this exposure of 1 hour time. Okay, so what does labeling this data look like within the app? I'm so glad you asked. It looks like this. Each one of those points is an arc that I found, except in this exposure.
I'm not seeing arcs.
I'm not either.
A couple.
Right? Like maybe some iffy ones. There are 4 different exposures, and they encourage you to cycle through all of them because as you do, some of those arcs become apparent. And then you can flip the...
Okay.
Yeah.
Ghost arcs.
There we go. Ghost arcs. Stolen. Okay. So you get a chance to really explore this data. This is at your own pace. You can spend as much time as you want with these 4 slides and their inverses. And you can cycle back and forth, double check yourself. You can, if you make a mistake, you can delete the point and start over. Okay, so clouds on Mars. Let's revisit those with a moment of zen.
Although, no, which craft took this?
This one is Perseverance.
Okay.
The original, the still that I showed you, those were that was Curiosity.
That was Curiosity. Okay. Well, what's cool about this one is you don't have to worry so much. You see an arc, you see something you think is an arc market. You're not going to be the only one doing it. Remember, there are dozens of people usually that are fed those same 4 images. So there are others that have your back. You miss an arc, somebody else is going to get it. You mark something that's not an arc, well, nobody else will mark it, and it'll get thrown out. So this is the way there are checks as we do these things. Well, I was looking for a project to show off to you, and I thought, well, let me do the Planet Hunter tests. That's, we had a guest here that talked about tests last year, was excited about it. Well, if you can see at the top there, the project was done. They didn't have any data for me. More will come. There will be more data to find, so keep this project in mind to do later. Then I thought, well, let's do Planet 9. Let's go search backyard worlds. We have Konstantin Batygin, who's Mike Brown's colleague. Konstantin's working on finding Planet 9. He's going to be here with us, by the way, in October as our guest. It'll be a lot of fun. But I had trouble with these noise maps, and I didn't know about the better one that Mark showed us, that it's easier to see them on. He said, yeah, people had trouble with this one, so they redid it. So I gave up on this, and I stared at some galaxies for a while. And I thought, well, let's just go back to the very beginning. Let's zoom in and look at some galaxy shapes. And there's all sorts of images out there with galaxies that need people to classify these. So let's go back to the beginning. Galaxy Zoo, it was one of the very, very first projects. This was what kicked off Zooniverse. So other than trying to find those little dust grains, this was the original project. So let me show you about it. Now, why are we doing this? Well, again, look at these images. Let's zoom into this little square here. All of those are galaxies. Almost every single little smudge you're seeing is a galaxy. And astronomers, we like to classify things. We like to know how many of each type are out there. Well, what do we mean by type? Way, way, way back, we originally thought galaxies would kind of easily separate into these. Things that looked elliptical, things that looked like spirals and had features, and then weird things, irregulars. Well, it's not that simple necessarily, but we're going to do some work to classify some galaxies, and you'll see the questions they ask are kind of leading us to finding out which of these this thing will be. So I started a project. Let's start one. And this is what it fed me. Now, you might think, boy, that's ugly. Yeah, it is. It's not very high resolution. But the ones we're looking at aren't. The Webb telescope is seeing galaxies at the very beginning of the universe, things that are, a billion years in age. The universe has barely been here. So these are galaxies that are just starting to get together. They're starting to form. Things are falling together. This is probably a merging pair, is my guess. So I looked at it and thought, well, I'm seeing features. This isn't just one big smooth thing. So I marked features. Click on it, and then you move on. And you say, okay, well, is it edge on, or is it something else? I was like, yeah, that's something else. This is not edge on. And then, well, what about it? Is there a bar feature? And I thought, yeah, maybe. If you look at this, there is sort of something that looks a little bit linear going through there. It was hard to see, but I thought, well, sure, let's mark weak bar. And again, I thought, maybe I'm the only one that sees this. Nobody else marks it. Well, then it won't get marked as a weak bar. That's okay. And then they wanted to know, are there signs of spiral arm pattern? Well, yeah, look at this. There's sort of a spiral there, and there's something coming off this direction. To me, it looks like in the upper right and the lower left, that's a spiral arm. So I wrote yes. And then they say, how many? Is it tight or is it loose? And I was like, well, it's loose. Those aren't tightly wound. They're kind of open. How many of them are there? Well, there's 2. There's 2 arms. So you mark 2 arms. Then they want to know, is there a bulge? So is there something in the center, sort of a fuzzy center? And it's like, yeah, there's a moderate bulge in there. I don't know what am I, an astronomer? Okay, I am. So I'm guessing. Yes, but again, you do your best. It's the first one I did, but to me it looks like there's a moderate bulge there. And then they wanted to know, are there any bright clumps, meaning little sort of speckles around it? Now, yeah, there's a bright clump in the middle and there's one down below, but I wrote no because I didn't think that's what they meant. I think they mean something else here. Now, why is this one yellow and bright? I don't know. I screenshotted it. This is how it came out, and I thought it was just meant to be. Now, is it merging? Is there something weird going on, a major disturbance, a minor disturbance? No, this thing is merging. This is a merging pair of galaxies, in my opinion. So I marked it as merging. And then they wanted to know, are there any gravitational arcs? Are there lenses? Are there rings? Are there any interesting features? Dust lanes? Nope, not seeing any of that at all. And I was done classifying. And then I thought, well, can I go find a galaxy online that looks kind of like this one, just for fun? I just wanted to. So it's over on the left there, and I started looking through them, and these are images of just galaxies, of Hubble program galaxies. And you can kind of look through it and say, well, there's one here, maybe. That's a disturbed one. There's a big arm coming off here. Here's another merging pair. So you can look in this panel of galaxies and pick out things that are sort of similar to what we see here. Not exact, but kind of. And that gives you confidence that, yeah, what I'm doing here is actually helping, because there are so many galaxies to find. Now, is any of this work doing any good? Yeah, here's the list of papers that have been published. It's something like 91 publications. It's crazy. I had to shrink it down to a font size of 5 so nobody can read that, but that's fine. And there are just galaxies everywhere we point. And that's why Galaxy Zoo is still going. The JWST telescope is taking these incredibly deep images. That's, I don't know if this is a Webb image. It's probably a Hubble image. But Webb, we need to classify those galaxies. And AI just is not very good at it yet. It just isn't. We've tried to write programs to do this. I had a friend in graduate school that was working on this and trying to write a routine to do it. It was able to get far enough, but just not past that final hurdle, especially now that we're looking at early galaxies with disturbances and mergers and everything else. So if you want to get involved with Galaxy Zoo, it's on Zooniverse. You can go to Zooniverse, just search for Galaxy Zoo, and it'll be right there, and you can find it. So we recommend that everybody get involved with citizen science. Go find a project you like to do. Go try it out. Worst case, go get BOINC. Get the screensavers going. I ran BOINC for a long time, too. I still have it loaded. I still run it. I used to run the SETI one, the one that was searching for extraterrestrial intelligence. They were using Arecibo data. It would just download, and I always thought, am I going to get credit for finding the aliens?
The LGM, yeah.
Yeah, I wanted to find the aliens, but I never did. So anyway, next month, by the way, we have another great guest in person. Sabrina Stiervold is going to be here. She's an Occidental professor. She has images of colliding galaxies from JWST. She's going to talk about her program. She's going to talk about how all that happens, and even maybe mention Galaxy Zoo a little bit. So come on back next month. Join us then. But first of all, I want to thank all of you for joining us. Thank you, Bill. Thank you, Sarah, for joining me on stage. Thank you, Mark, if you're still out there. And as always, All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, and the City of Los Angeles. And again, we'd like to thank our exclusive nonprofit partner, Griffith Observatory Foundation. And we thank all of you for joining us here tonight. Thank you, everybody.